Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to full adder combinational arithmetic circuits. Previously we discussed the implementation of full adder using NAND universal gates. So in this video we are going to discuss the full adder implementation using NOR gates. Okay, this. Okay, so before that, first the block diagram of full adder. Three inputs, the two bits to be added, A and B, and the input carry. The two outputs, sum and carry out. Sum, we will write it as A XOR B XOR C in this format. And there is a reason why I am writing it in this format, because we will be using this format for simplification using NOR gates. Implementation using NOR gates. Then carry out we will write specifically in this format. AB or A XOR B into C. Okay, this format. So let us see how we can implement these expressions. Okay, first for the sum part. Okay, A XOR B XOR C. This is sum. Okay, now if we consider only this A XOR B part, and let's call it as X, that is A XOR B is equal to X. So now A XOR B if we do the double complement of it, it will essentially be the same thing, because the double complement of a variable is the same variable we get. So we can write it as A bar B or AB bar double complement. Okay, this double complement. So it is equal to, here we'll apply De Morgan's theorem, which is this: X or Y whole complement is equal to X complement and Y complement. This De Morgan's theorem we will apply here. So here it will be equal to A bar B whole complement and A B bar whole complement for this inner complement, and then the upper complement or the outer complement, this. Okay, now another De Morgan's theorem, which is X and Y whole complement is X complement or Y complement, that we can apply to these two inner complements, this and the entire complement, which is in the form of AND. See here, there is AND, and this is AND. So we can apply De Morgan's theorem, this second De Morgan's theorem, to this one, and the entire this whole complement. Okay, so how we'll do this? See. So first applying them to the inner complements. So it will be A double complement or B complement and A complement or B double complement, then whole complement. So double complement of a variable, we get the same variable back, so it is A or B complement, then and A complement or B, then whole complement, then A. So now we have this A or B bar and A bar or B whole complement. So again we'll apply De Morgan's theorem, this one, to get the expression A or B bar whole complement or A bar or B whole complement. This. Okay, so this is what? This is A XOR B, which is equal to X. Okay, so this is very important. So this is only X here. From here to here we have got this. So why we converted into this form? Because for NOR implementation, every variable, every term and the entire thing, expressions, should be in OR with a complement, OR form and with a complement. So that is required. So this can be implemented using NOR. Now we have the sum of the full adder, it is A XOR B XOR Cn. Now this much portion A XOR B is X, so we can write it as X XOR Cn. So again we can do X XOR Cn is equal to X XOR Cn double complement, again the entire thing X bar Cn or X Cn bar, and just substitute A with X, B with Cn. Okay, substitute A with X, B with Cn, and we'll arrive at the same expression, which will be in this format. So this is what? This is sum. So finally we can write the sum as X S is X or Cn bar whole complement or X bar or Cn whole complement. Okay, this is the final expression of sum which we have to implement. X or Cn bar or X bar or Cn whole complement. Okay, this we have to implement. So let us implement this. Okay, first now secondly let us simplify in the same way the carry expression. So carry is for C out, output carry C out. C out is AB or A XOR B into and Cn. So if we do double complement of it, we'll get the same thing, C out, which is AB or A XOR B into C in double complement. Okay, double complement. Now A XOR B is what we have just proved. A XOR B is X. So it will be easier if we substitute this with X. So we can write it as AB or X C in double complement. So now we can apply again De Morgan's theorem to it, and we'll get AB complement and X C in complement, whole complement, this. Now again we can apply De Morgan's theorem to this and the entire thing. So it will be A bar or B bar and X bar or C in bar, then whole complement. Again applying De Morgan's theorem here, we'll get A bar or B bar whole complement or X bar or C in bar whole complement. So we just applied De Morgan's theorem, this one, okay, and Y whole complement is X complement or Y complement. This one we applied successively. So we finally have arrived at the expression of carry out, which we'll be using for implementation using NOR gates, because everything is in OR format and complement format. Okay, this. So now what we have to do is we have to implement this logic diagram using NOR gates. Okay, so let us do that. First for sum and then for carry. So again just write down the expression of sum. Sum is X or C in bar or this is whole complement or X bar or C in whole complement, and where X is A or B bar whole complement or A bar or B whole complement, this. Okay, so first we have to get X. So here we'll take A and then B. Okay, then we'll get A bar then we'll get B bar. A or B bar whole complement. A or B bar. Okay. A so this is A or B bar whole complement. Then A bar or B complement. So this is A bar or B complement. then we need this, the sum of these two. So how we'll get it? We'll add them first together. The result will be A bar or B complement, or A or B bar complement, then whole complement, because it is NOR. Then again, if we pass it through the same NOR gate, we'll get this A or B bar complement, or A bar or B whole complement, because this upper complement will be removed. So this is X. We have got X. So now what we need to do is we need to get the expression of sum, which is the final sum expression of full adder, which is S is X or C in bar whole complement, or X bar or C in whole complement. So we'll take here X from here, okay, and we'll take C in. So first we'll take the complement of X, so it is X bar, and then the complement of C in, which is C in bar, in the same manner. So we will repeat this entire thing again. So again, X bar or C in whole complement, then X this is X or C in bar whole complement. Then again we have to pass them through a NOR gate, and we'll get X bar or C in whole complement, or X or C in bar whole complement, and again if we pass them through another NOR gate, this upper complement will be removed. So finally we'll get X bar or C in whole complement, it's not really okay. X bar or C in whole complement, or X or C in bar whole complement, which is the final sum expression which we need. This. Okay, this is the sum. Next we need the carry, which is A bar or B bar whole complement, then X bar or C in bar whole complement. This is the sum. Then we have carry from here, which we got. Okay, A bar or B bar whole complement, or X bar or C in bar whole complement. So I will show it in a separate logic diagram, because if I involve it here, then it will be a bit complicated. So what we'll do for the carry part, we'll take directly from A bar, we'll take where we have done A bar, we'll take directly A bar, because we already have A bar here. We have already A bar here on the upper side. So we'll take A bar from here, this let me draw it from here. Okay, this is A bar, so we can take A bar from here. This is A bar, then we'll take B bar from here. Okay, that's why I am trying to draw it separately. We'll take B bar here. Then we need X bar and C in bar. So here this is C in bar. So we'll take C in bar from here and we'll take X bar. This is X and this is X bar. And this is X bar. Okay, from here. That's why I'm drawing it separately. So A bar or B bar whole complement. So this it is A bar or B bar whole complement, then X bar or C in bar whole complement. Then we'll again pass it through another NOR gate and again through another NOR gate, because the output of this will be A bar or B bar whole complement or X bar or C in bar whole complement, then whole complement. So in order to remove this upper complement, we have to get, this is X bar or C in bar whole complement, this. So in order to remove this upper complement, we have to pass it through another NOR gate, which will get finally A bar or B bar whole complement, X bar, C in bar whole complement, which is the final carry expression. So here, because of lack of space, I had to draw it separately. So we had to use extra 1, 2, 3, 4 NOR gates. Okay, we took A bar, B bar, X bar, C in bar. We got A bar or B bar whole complement, X bar or C in bar whole complement. We passed it through a NOR gate here, which we got this. In order to remove this upper complement, we had to pass it through another NOR gate, and we finally got the carry expression. A bar or B bar whole complement or X bar or C in bar whole complement. And always remember, here X is nothing but A XOR B. This. Always remember this. This X is nothing but A XOR B. Okay, so this is the implementation of full adder using NOR universal gates. Now I know that this can be a bit lengthy, a bit messy, but you have to be careful where you take the input and output lines from and draw the logic diagram with a bit of a, with patience and bit care, and you will arrive at the correct result. Okay, so this is the